Hello everyone, how's it going? My name is Dan the Tutor, on a quest to become the world's greatest tutor. In today's video, we're going to be talking about the derivatives of exponential functions. So we're talking about the derivatives of functions like this. E to the x, e to the 5x, and even ones like 2 to the 10x minus 7, or something crazy like that. Now the cool thing about these functions, obviously as you can tell, the x is in the exponent for all of these. That's what makes it an exponential function. X is in the exponent. If you ever see something like this, x to the power of x, this is no longer exponential. If you want to find this derivative, you would have to use something called logarithmic differentiation, which I'll be covering in a different video, so not this one. So before we talk about these derivatives, just a really quick note. I know this is not necessary, but you should know this. The number e, Euler's number, named after the greatest mathematician of all time, Leonard Euler, as a decimal is 2.71828 ... It's a number that goes on forever, like pi. This number that you've almost certainly seen in pre-calc or algebra 2, this number is finally going to matter for calculus. And the reason why is because this number e, 2.71828 yada yada yada, its exponential curve, which is e to the x, is the derivative of itself. In other words, if the function f of x is e to the x, and I want to find f prime of x, it is the only function in the world whose derivative is the same as itself. Which is pretty cool, and you can disagree with me, but whatever. And if you were to take the second derivative, it would also be e to the x. And if you were to take the third derivative and the 10th derivative, you can just keep going down the list. It's always going to be e to the x for your derivatives. But what if you have something like this? F of x equals e to the 5x. Well, now the chain rule is getting involved because this derivative in the exponent is no longer just 1. So if you want to take the derivative of this where the exponent is basically anything except a plain old x, then the answer is rewrite the original, e to the 5x. That part stays the same. But now, because of the chain rule, I have to multiply by the derivative of my exponent. The derivative of 5x is just 5 because of the coefficient rule. And now, there's my answer. And if you don't like writing it like this, and instead you want to write it as 5e to the 5x, then that's absolutely okay. You can do that. It's the exact same thing. So then, why don't you try this one on for size? F of x equals e to the x squared plus 2x. Go ahead, give this a try on your own. If you get stuck, then watch the solution for how I do it. Okay, so here's what we do. F prime of x equals, first things first, I'm just going to literally rewrite the original function because that will always be part of the answer. And then I have to multiply by the chain rule the derivative of x squared plus 2x, which has to go in parentheses because it's a quantity, and the derivative of that will be 2x plus 2. And I don't have to do anything with this. I don't have to distribute it. I can just leave it like this, and we're done. Very simple. But then what if I have this? F of x equals 2 to the x, where it's no longer e. Well, that is going to be a problem because only e works with that super simple shortcut rule. But the good news is if it's not e in the base, and it's something like 2, there's a very simple fix. So first, f prime of x equals, again, rewrite it. That part stays the same. If I think about the chain rule, or the derivative of x, is just 1, so that doesn't really matter. And then finally, this part's new, you have to multiply by the natural log of your base, which in this case is 2. And you can write this in a few different ways, but this is going to be our answer, and that's it. Now the reason why this works so nicely for just plain old e to the x is because what's the natural log of e? Well, that's just 1. And so for that reason, I don't need to say times natural log of e at the end, because that's just 1, and 1 times anything is the same number. So that's why this rule still works, and that's why we love the number e. It's our favorite number in calculus, or at least my favorite number. And so now there's just a couple more cases I do want to mention. Like for instance, what if I have something like g of x equals e to the 7x times e to the 2x? One thing you could do is you could do a product rule because it's two functions multiplied by each other. But I would recommend doing this instead. Properties of exponents say as long as the base is the same, then you can add the exponents. So in other words, this is e to the 7x plus 2x, which is really e to the 9x. And by the way, that's exactly why we learned about properties of exponents back in pre-calculus and algebra 2. It's literally so that one day, when we get to calculus, you can do the simplification trick and find the derivative very easily. As a matter of fact, I would make the argument that almost everything you learned in pre-calc, and even most of the stuff you learned in algebra 2, is literally just to prepare you for calculus. Calculus is like the final boss at the end of your long, long math career, where you have to use all of the little tricks you've accumulated over the years to solve problems like this. Which I think is very cool. A lot of students think it's stupid and you'll never need calculus in real life, so why does this ever matter? And those students, of course, have a point, but at the same time, if you think that, you're just a loser. And we're not losers, we're winners, so we're not going to think like those students. Anyways, we still have not taken the derivative yet, so finally, g prime of x, the derivative, is e to the 9x, just rewrite it, and then times the chain rule, which is 9. And there we go, there's our derivative. You can also do this for more complicated ones, such as y equals 5 to the power of 4x plus 1 divided by 5 to the power of negative x plus 6. And one thing you could do is the quotient rule. This quotient rule would be very long and very terrible. So instead, I recommend using our properties of exponents. Specifically, since the bases are the same, they're both 5, you can simply subtract the exponents. You do have to be very careful with this because notice how I'm putting the denominator in parentheses. I would then distribute the negative sign before I combine like terms. I would do this in 2 steps, not 1 step. And you'd get 4x plus 1 plus x minus 6. Combining those like terms in the exponent would get me 5 to the power of 5x minus 5. Whole lot of 5s here. And then finally, I would take the derivative. Well, let's see if you can get it on your own first. Go ahead, pause the video, see if you can get it. Okay, here's what I would say. First, rewrite it, 5 to the 5x minus 5. Then times the chain rule. Derivative of 5x minus 5 is just 5. And then finally, times the natural log of 5. And if you're wondering if any of this stuff can be combined, the answer is usually no. But this is a silly example because the 2 base 5s here are the same base. This normally doesn't happen. And since this is technically 5 to the power of 1, you can combine these to give yourself 5 to the 5x. Negative 5 plus 1 is now minus 4 times the natural log of 5. And there's our final answer. But if you left it in this form right here, that's how we're going to leave it 99% of the time because the bases will be different. It won't be both 5. So I would say both answers are correct. And that's all the problems I wanted to look at today. Thank you all for watching. If you have any questions, please post them in the comments below. Have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.